how it's tried. All right, so here's the difference between optimizing and related rates. With the related rates problem, you have some geometric reality, and one thing is changing, and you're looking at how that change is affecting one of the other measurements. So I'm blowing up a balloon, and my radius is changing. How does my volume of that balloon changing? I'm sliding a ladder, and the distance away from the wall is changing. How is the distance coming down the wall changing? So when we talk about related rates, we have some geometric story. Pythagoras, area, volume. And in that story, one of my variables is changing, and I'm looking at the impact that that change has on one of the other variables. So I've got two things changing at the same time, related rates. And your equations require implicit differentiation, because you're going to just differentiate the equation as it's given to you. And when you have an equation for related rates, your number one job is going to be to rewrite that equation using just that one variable. So that's going to be anytime that you can rewrite the equation in terms of one of the other variables, then that is just less things for you to have to solve for. With optimization, we take it one level further, and we say, okay, we recognize that how these two things are coordinating with each other changes either my area, my volume, my cost, my profit, my, whatever that outcome is. And what I want to do is I want to optimize it. Meaning I want to find the height of that curve or that bottom of that curve, whether I'm talking about a maximum or a minimum. So as soon as I take the derivative, you're going to be setting it equal to 0 because you're going to optimize that, and that happens when my tangent line is equal to 0, when the slope of my tangent line is equal to 0, that rate of change. So you're looking for either that maximum or that minimum part of the graph, and we know that that happens when the slope of the tangent line is equal to 0. So if we're looking at that graphically, if I have some kind of a curve in my graph, I'm looking for this part here where the slope of my tangent line is either maximized or minimized. And the nature of your equation and the relationship between the values in that equation is going to naturally give you that maximum that you want to try to find the height of, or that minimum that you're looking for. So yours is not to worry about whether it's a maximum or a minimum. You just need to know that you're looking for where the slope of that tangent line is equal to 0. Where do I have one of those horizontal lines? When I take the derivative. So you take the derivative, you set the derivative equal to 0 to figure out what xy values are going to make that happen. So the related rates, one thing is changing comparing to the other, and you're looking for that other rate. Optimizing is where you are taking that equation and you are looking for where's the derivative equal to 0. Does that help a little bit? We talk about it at the same time. All right, so in these in our first optimization lesson, all we had to do was write the equations. In this optimization lesson, you are defining your variables, you're writing your equations, and you're coming up with just one variable so that, notice when I'm taking my derivative, it's not with respect to time. So your related rates is you're looking for the change in this with respect to time. This, I'm just taking my derivative because I got it down to one variable, so I don't have to worry about the dx dt because it's a derivative in terms of x. So I don't have all those extra rates embedded in. This should not surprise you, because if you did the Desmos, you saw that the more square your figure, the more the maximum the product or your area is that you get. So it's a classic banquet table problem for entertaining. So my son got married last year, and when you look at how you want the number of guests to fit in any space, the round tables are the least efficient as far as maximizing area. Because your round tables will maximize area and minimize perimeter. So when you go to a function and you're seated at a round table is optimum for guests hanging out and having a really good time. But if people are looking to gain more space, they can fit more people around a long skinny table. That's why the tables that you eat at in the cafeteria are long skinny tables.
Well, they have circle ones.
They're circle.
Even the long skinny
They changed the
wavy.
answer.
You don't have any long skinny tables?
No. They're like the ones in elementary school, they're like round, like people sit around, that's what we have now.
Yeah.
You mean all the way down? Yeah, all the
When
way
did they get rid of them?
They're like curly, curvy.
It's just all round.
What?
Yeah.
I don't know why they did it.
And now we can't fit as many of you in the cafeteria.
Yep, yeah,
Yeah.
no, literally, yeah.
Is there not enough seats?
I have to sit in the foyer because.
Oh, stop, we need to go do some, we need to like take a field trip and go do some measurements.
They're not gonna do that.
No, we can do that.
Yeah.
Because,
Yeah, we know.
okay, I gotta go for a, okay, wait a minute, stop. I gotta go for a walk and test that out this afternoon, because what used to be last month when I was in the cafeteria last, long skinny tables. And everybody could fit in the cafeteria because they minimize area and maximize perimeter. As soon as you blow that table out and you make a square table or a round table with the same dimensions, right? Are you okay with me with the square and round being the same conversation? You are maximizing the area and minimizing perimeter. So y'all can't fit in the cafeteria anymore.
Yeah.
And the seats are attached to the table.
Well, I
Shut the
would have
front
been
door.
okay. They're like
They're
round
very little,
seats,
yeah.
and
They
I
don't
thought they would,
swivel.
I thought they would move. I was like, okay, maybe it'd be a bonus that I
Yeah,
can
it's
like
like a
move.
stool.
Nope, they don't.
It's like a stool
It's like a
attached
short
to the.
stool.
Yeah, so then they don't have all the separate chairs.
No.
Yeah, but now they're
The
just
chairs are
lined
so
up
much
on the
bigger.
wall in like the hallway.
I know
Amount of
like
times I
people-
hit my shins.
Wow.
I was sitting next to Toby.
Right? So we're gonna write a letter to whoever's in charge of that and say, did you know that when you took the long skinny banquet tables out, you maximized your area and you minimized your perimeter? And you can think about
Look at this.
that perimeter of each of those tables, represents a seat, right? So, for example, if I have a box, okay, let's say that I have a 24 by 1, right? So, and then we can compare that to a 12 by 2. I should have picked number, it's a perfect square, hold on. 36 by 1. Help me out with my math. 18 by 2 versus 12 by 3 versus 9 by 4. Obviously, my picture is not accurate. Versus a 6 by 6, right? All of those have the same area of 36. But if you're talking about seats that you could sit people at, if you put 36 people on one side here, I mean, depending on how skinny you want, right? So let's say that here, I put 18, 36 and 1, let's just talk about perimeter, is twice 37, right? Here our perimeter is twice 20. Here our perimeter is twice 15, do you see the pattern? Here our perimeter is twice 13, and here our perimeter is twice 12. So look how many old tables, new table. Are you with me on each of those measurements? So we keep changing it around about, I'm maximizing the area of my pig pen, or I'm maximizing the perimeter of my fencing. Like, there's only so many ways we can talk about the same area perimeter conversations. But our derivative understanding of it is huge. When we talk about what we want, are you looking to minimize? Are you looking to maximize? Are you solving with respect to area? Are you solving with respect to perimeter? And whichever equation, so think about this for a minute. If you're confused about this optimization, area equals length times width, perimeter equals twice width plus twice length. Those two equations both involve relationships between length and width. If you're confused about which one to plug into the other, which one are you optimizing? Are you looking for your maximum perimeter? Then you're substituting these values into this and taking the derivative of this. Are you optimizing area? Then you're putting your values into here and substituting into here. Because both of these relationships involve lengths and width. But whatever value that you're optimizing, perimeter area, that's the equation you're taking the derivative of. That's the one you're setting equal to 0. That's the one that's going to tell you graphically when your derivative has maxed or minned out. Does that help a little bit? We're taking a field trip. Not today. But I'm gonna talk to Miss Holdaway and we're gonna go for a walk. Because the fact that they changed out those tables and I had no idea freaks me out a little bit. Well, we don't have staff meetings in person anymore, so at the beginning of the year, we all went down, and I know I sat at those long tables. Yeah, and now we're all online for our staff meetings because of the COVID. We have to do Zooming, so I haven't been down to the cafeteria in a long time. So are you telling me when you go to eat, there's not enough tables? There's not enough room?
Like, it's like, because we do have like office, but they're like wavy, but the still seating isn't clear. Because they like
You can't even add more chairs.
Yeah,
It's
exactly.
just a given number of chairs,
Exactly.
because they're attached.
That's
But
why,
there are a few long tables?
Oh,
Maybe
yeah.
how?
it's like,
Like, they
they're
go
long
like
tables,
this.
but they're like
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 wavy.
way-
if there's a line of kids and I'm over here, my friend would be like back here, so back on top.
It's like, wait, but.
Now I gotta go for a walk today.
You should go right now.
That's crazy to me.
Why not the?
Yeah.
Not now.
So much better.
Look at the list of things we have to do today. Okay. Okay, so here we go. Our rancher has 200 feet of fencing and 2 adjacent rectangular corrals. And notice, when you draw this picture, I was disappointed. I checked my equation time and time again because I didn't like the fact that these weren't friendly numbers. I think Ms. Holdaway used X's and Y's instead of lengths and widths. But then we can talk about, because we're looking to maximize our area, we take this equation and we fold it into this one. And then we take the derivative, set it equal to 0. And that's what gives us our answers. All right, on the back, a production facility is making face masks. When they give you the equation, you just go with what they give you. Please make sure that I can see the difference between your equation and your derivative. So remember when we thought about that? It matters. So that everybody who's looking at your work can understand, here's my initial equation, here's where I took the derivative of it, here's where I set the derivative equal to 0, and then here's where I solved for x. I did a proportion with cross products to get my x out of the denominator. These distances to the closest point problems, I have my distance formula. My 2 points are the one they gave me, and whatever input output comes from my equation that is of my graph. And then depending on up until here, when we talk about finding my derivative here, I'm just neatening it up, combining all my terms, and then here is where I take my derivative. And the chain rule, this to the less power from the derivative of what's inside. Now, this is a huge conversation here because this is kind of a beautiful thing because you get real ugly down here in the denominator, and then you kind of realize, I don't care about that. Do you know why? Do you know why you don't care about that? Because this equation is true when my numerator is equal to 0. So this is the difference of two perfect cubes, which factors into that. This is my easy factor. And this one, you can always, like, I don't know if you remember that from Algebra 2, but that was always prime, and you couldn't factor it, and it didn't, there were no real roots for that one. So that was never equal to 0. So that's what the point is. And this is a really cool, interesting problem, and she ended up, any of you go watch Mission Impossible, just to see that clip for the Tom Cruise thing. She was obsessed with it in her part of the lesson. But it was hard because when I did the homework first, she and I set up all of our variables differently. So if you set it up like hers, it doesn't match mine. Okay. So here's our so what, now what for today. Here we are today. This homework is practice for optimization. And you are at one of 3 different states of doneness with this homework. You are, number 1, I did it and I want to check my answers. You're group 1. Group 2 is I started it, I'm not sure I get it, I need some support. I got a couple specific questions and then I'll be ready to check my answers. You're group 2. Group 3 is, I don't even look at it, I gotta be honest with you. So mine's completely blank. So you're group 3. So different states have done this. Does group 1, 2, or 3 describe all of you? Anybody not able to put themselves into a group of 1 or 2 or 3? What would group 4 be?
I lost it and it's just gone.
Well, I gave you a new one, so I don't know. That's that. I'm pretty sure I said enough to include everybody, but I wanted to make sure. All right. So, if you're group 1, you can come see me for a key. And then you can check your answer. If you're group 2, I want you to come up and ask me your question. And then we'll talk about the answer. Please let me keep talking. If you're group 1, come see me for a key. If you're group 2, come up and ask me your question, and then you can fix your work. If you're group 3, get busy. Do the work, and then come see me when you're done. Hold on. On the back is that related rates review. So the front is optimization, and the back is related rates. Does that make sense, everybody? Have a seat. After you finish your homework, and you check in with me, then I want you to log on and finish your Desmos. If you're finished the Desmos, then you're ready to build a box with that maximum volume. The build a box with the maximum volume includes the materials that are on the back round table. So when you look on the back round table, we have scissors, cardboard, and rulers. I'm hoping that that's all you'll need. What we'd like you to do is decide how you want to optimize the box. So you're going to build an open-end box that looks like this. The tape and the scissors and the rulers and the paper will all be back there. You're going to measure and cut squares from the corner, and you're going to fold to create the sides and tape the edges together. If you use one of your squares as a cutout, it can be a template to make sure that it matches all the other ones. Your goal is to find the one that has the greatest volume. Does that make sense? Okay. So I'll leave this up on the screen to help those who need to see it. Questions before I let you go work? Go. All right, so when we talked about this box, these boxes, which one has the greater perimeter or the largest perimeter? Let's just say I pick B. And then I go through, what are the rectangles by area? Let's say I thought B has the biggest area. Then C, then they're like, oh, snap, they all have the same area. Or a fun fact, they all have the same perimeter. What is the perimeter? So they each have a perimeter of, what does this put you at, 50? Right? So what's really cool, they do not all have the same area, which is the greatest area. And we talked about this before. The greatest area is B, which is 150, right? So when you share with the class, I don't know if you were able to see other people's responses. And then you played with, I'm hoping that you got some value out of playing with, and I'm having a hard time seeing my whole thing, so if I make this smaller, if I go to change my field, I can make it 50, I can make it 50, and then I could make it 50. Make field C as big as possible. Didn't I already make it? Is it gonna let me do that? Okay. When you filled in your lengths and your widths, what we wanted to see was, and you sketched your relationship. Oh there. That's crazy. What I'm hoping, that means you guys failed at graphing. It should have been an upside down quadratic. If I look at a summary, I can see all your graphs. Let me go back and look at this one, what your sketches were. Oh dear. Oh boy. So with this page, what they wanted you to do was your annual field, right? And we wanted you to look at and have that conversation about that maximizing. Click and drag the quarter fence to make your biggest field. What you wanted if the square your field is the maximum area. That was the whole idea. Maybe go back and revisit your Desmos. That counts as a homework, classwork grade. So if you're looking to give your grade a bump, go back and give it the old look over and make sure you did a good job. I'll post a key, test next class. You'll get your quizzes back and we'll talk about them and go over them. Sound okay? Did everybody get a donut?
How about you?
Hmm?
How about you?
You're about to.
Thank you.
You're welcome.
You say the water.